All right, today we are going to talk through chemical equilibrium and what it is and how we can quantify whether or not something is in equilibrium. So, chemical equilibrium happens when the forward rate of a reaction is equal to the backwards rate of the reaction. It does not mean the amount of products is equal to the amount of reactants. So that is something that confuses students quite often, and you need to make sure that that is not what you're getting in your head. It is when the forward rate equals the backwards rate, not that the concentrations are equal. So we're going to be working with this standard chemical reaction here, this generalized one. And what I want you to notice is that when we look at this generalized chemical reaction, the arrow is different than what we've seen before. The arrow is a double-sided arrow. You might also see it looking like this, but I quite often use the half harpoons to show that there's two different reactions going on. So what this is showing is that we have a forward reaction, which we are used to seeing, and then we also have a reverse reaction, so where our products are turning back into reactants. And the majority of reactions are actually reversible. There's very few that don't have that reversibility. And the way that we quantify if something is at equilibrium is that we write what's called an equilibrium expression. And we have our equilibrium constant, which we symbolize as KEQ. And the way that this is written is that we are going to put the concentrations of our products over the concentrations of our reactants. So the way we represent that is that we have, I'm going to do this. I'm going to underline our coefficients in blue. And then we've got our actual species in red. So we have concentration represented by brackets. Okay. And as I said, we're going to do our products on bottom. So we've got our product D and our product C, and then we're going to take the coefficients, and those are actually going to become exponents. So they're going to be powers of our concentration. So we're going to treat them as exponents. And we're going to do the same thing on the bottom. We're going to use brackets to represent concentration. And we've got reactant A and reactant B, and then their coefficients are going to become exponents. And there is an implied multiplication in between them. We're going to remember our order of operations in that we raise things to a power before we multiply. And a special caveat here, or a thing to remember, is that we are only going to include aqueous, so it's labeled AQ, and gases. If it's solid or a liquid, it's not included in the expression. So I'm going to walk you through an example here, and then we'll explain what these mean. So our example here that we have is we have sodium bicarbonate reacting with water to form a bicarbonate ion and a hydronium ion. My recommendation to you is when you get things like this, I want you to immediately cross off anywhere where you have a solid or a liquid, because it's not going to be included in our equilibrium expression. And then what I want you to do is make sure you understand which are your products, which are going to go on top, and which are your reactants, which will go on bottom. So reactants are always on the left side, products are always on the right. Now I'm going to put in my expression. I have HCO3 with a minus sign. It does not have a coefficient, so it's going to just be 1 times H3O plus, also doesn't have a coefficient. And then for our reactant, that is going to be the concentration of H2CO3. And once again, that doesn't have a coefficient. So those are the concentrations put in. And now over here, we have a nice little data table that gives us the concentrations at equilibrium. So I am going to take my information here. This says for the sodium, for the bicarbonate, or maybe carbonic acid, hydrogen bicarbonate, you would have 3.3 times 10 to the negative second on the bottom. I don't know why that doesn't want to go. And then on top, we're going to have our bicarbonate concentration times our hydronium concentration. And I want you to notice that these two are the same. So I'm going to effectively write it as 1.19 times 10 to the negative fourth. And I'm going to square that. Okay, because if I multiply a number by itself, it ends up being that number squared. And now we can just type it into our calculator to get the actual value of our equilibrium constant. If we do that, let's see, I'm trying to find my calculator. Mrs. Burwitz, you need to be prepared, or better prepared. So I'm going to type in 1.19, and then I'm going to use my exponent, my engineering exponent. So push that second 10 to the negative 1 button on your calculator so I get a capital E. And then I'm going to square that, and then I'm going to divide it by 3.3. Once again, engineering exponent, negative 2. And I just realized I forgot to make that a negative 4 in here, so I need to insert a negative up on the top. What I am left with is 4.29 times 10 to the negative 7th. Wonderful thing about equilibrium constants, no label. These numbers are allowed to be naked. Now, what does this mean for us? If an equilibrium constant is less than 1, okay, we've got a negative exponent, negative power of 10. There are more reactants than products at equilibrium. So the reverse reaction is favored. or reactants are favored. If our KEQ is greater than 1, so we have 10 to a positive power, whereas over here it would be times 10 to some negative power. That means we have more products than reactants at equilibrium, so the forward reaction is favored, or products are favored. So you need to be able to solve for KEQ and determine what is favored. Looking back up here, you'll notice we've got a negative exponent. So that means that our reactants are favored. Once again, that dead pixel on my computer is making me suffer. So let's scroll up so I can get out of that dead pixel. Or you can say that the reverse reaction is favored. Both of those are correct. So you will have some problems on formative to work on. And make sure you're paying attention to what your products and your reactants are, and make sure you're paying attention to those signs of your exponents, if they're positive or negative. Don't forget those negatives. That's always the trickiest bit. Thank you for listening.